Hello everyone, welcome back to ECE350 again. And this is lecture 16. This is the last lecture for chapter 6. From the next lecture, we're going to go into chapter 7. So in this lecture, we're going to talk about displacement current. This is a new concept, new term for all of you. So if you look back into Maxwell equation, this one over here, this is the original Maxwell equation, right? So this part over here, if you take the integration on both part, if you take the integrate on the both side over the surface, this side over here can be written with this equation over here using Stokes theorem. So this is your Ampere's law, which is current, right? So that means this one could be replaced with this one right here, right? Then this side, if we integrate, this is the current density. If we integrate over a surface, you get the current, which is called conduction current. That's what we know so far. And what is this one then? So this side is current. This is the current over here, total current. We have a current IC, conduction current. There's another current over here. So what is this? Maxwell came across this term in when I think it's 1873. Yeah, 1873, when he was working on this his force satisfaction equation. So now he named this term as called displacement current. So displacement current does not involve real charges, but is acts like a real current. Okay, it acts like a real current. So this one we have a displacement current now. ID is basically this equation over here. Surface integration of dd by dt dot ds. Ds is the differential area vector, and d is the current flux density. All right. So current has two components now, IC and ID. IC is the conduction current, ID is the displacement current. Okay, let's, how do you understand this? To understand this thing, we can examine a parallel plate capacitor, who is a good example for understanding both currents. So for a parallel plate capacitor, we are using a ideal conductor here, ideal conductor and ideal dielectric. So ideal conductor and also using ideal dielectric. Right? So over here in the surface, as imaginary surface S1, over here ideal conductor. For ideal conductor, we don't have any electric field inside the ideal conductor. So electric field is 0, D is 0, right? If D is 0, you know that, if you go back here, you know that your displacement current involves a D. If D is 0, your displacement current is 0. That means there is no displacement current over here. To find the current now, whatever current it is here, to find the current over here, I have to rely on circuit theory. Circuit theory says that voltage across basically Ohm's law, voltage across impedance divided by the impedance will give you the current, right? So the current to the capacitor over here can also be written as this one here. So I1 C1 is the same current coming from here, right? C dVGC, if we do the math, you got this equation over here, right? So for the surface S1, your current has IC1 and ID1. ID1 is 0, so you have only IC1, that's I1, that's basically right here. You can also see it as our circuitry over here, VC over XC will give you the IC1 because that's the same current coming from here. So VC is the same voltage as the source voltage because nothing in between them. I have ideal conductor, so there's no drop there, and over capacitive impedance, right? So then if you do the math, it's going to come to this one here. What is J? J is basically 90 degree, right? So you can take the J out of here, put 90 degree back here. Now if you do the trigonometry, it becomes this equation over here. So that's the same equation, right? You can get the answer in both ways. So there's a current going through this imaginary surface S1, which is conduction current, which is basically negative omega C V0 sine omega t. So that's at surface S1. If I have another imaginary surface S2 in between two parallel plate, again, in between two parallel plate, we have the ideal dielectric. Ideal dielectric has the conductivity 0. If the conductivity 0, there is no conduction current, right? So now to find the current going over here, I have to find the electric field between them. Electric field is basically voltage over distance. So that is right here, and it's in the y direction. It's in the y direction here. Then to find the D, electric flux density, this is epsilon times C. So epsilon times E is right here. So now we can use this D into the equation for displacement current right here, right? And ds is your differential area vector, the direction in the y direction, so y dot y will give you 1. Then you do the derivative and also integration over here, you will get this one. So this is the current going through the capacitor. This is basically your only displacement current, because capacitor doesn't have any conduction current because you're using ideal dielectric, right? So that means IC1 is equal to I2, I1 is equal to I2D, and that's basically I1 equal to I2. So that is basically, so now if you have something capacitor like this, if you have a capacitor that is not made out of ideal materials, so you might have some resistance and also capacitor part here, right? So to 12 current over here, so whatever current goes over here will be IC, whatever current goes over here will be ID. So then your I would be IC plus ID. So pure capacitor only has the displacement current, and the impurity in capacitor could be a resistor in parallel with the capacitor that will have the conduction current. If you add that both, you get the total current. All right, we're going to look for this review question in the class, and we're going to solve this problem in the class too. That's all for lecture 16. We're going to see you guys for lecture 16 or 17. I think 16, right? Then for the next class, we're going to start the new chapter 7.